In this video, we are going to discuss some applications of the ideas that we discussed in the previous video on the behavior of conductors in electrostatic conditions. Today's video is going to be about applications of that concept, of those concepts, and then after taking up a few applications, we'll move on to the most important applications of these ideas, and that is the study of capacitors. So let's get going with this. To start with, just a few very elementary kind of applications of what we have discussed in the previous video. Let's imagine that we have a charged particle Q here, and we have a metallic uncharged sphere over here. Now it could be solid, it could be a shell, doesn't really matter. The radius is r, and this sphere is kept at a distance r from the point charge, or let's say the charge is at a distance small r from the center of the sphere, and of course this small r is given to be greater than the radius capital R over here. Now the question we are asked is that we have to calculate the field, electric field that is, at the center of the sphere, at the center of the sphere. Now you already have an answer to this question in your mind, and you're saying the field at the center of the sphere is 0. Of course that's correct, but this is not the complete question. Let me complete it. Electric field at the center of the sphere due to the induced charges, right? So that's our question here. Now obviously the electric field at the center of the sphere, because of this charge, will be in this direction. I'm assuming it's a positive charge, so that field will be 1 by 4 pi epsilon naught times q by small r square. Now the charges induced on the surface here will be somewhat like this. We'll have some negative charge induced here, negative charge pulled in by the charge here, and some positive charge over here. Now this is the electric field due to charge Q, or you can say the external electric field at the center of this sphere. Now the electric field due to the induced charges has to be exactly equal and opposite to this field. So the electric field due to the induced charges will be equal to 1 by 4 pi epsilon naught times q by r square, exactly opposite to this but having the same magnitude, so that the net field here becomes 0. So that's a very simple problem, just a warm-up problem for this class. I'll modify it. Let's make a small change here and have a somewhat more interesting problem. Suppose this time we have the same charge Q at the same distance. We have this sphere of radius r, the distance of this charge from the center of the sphere is same, small r, so pretty similar setup, but we introduce a small change this time. What we do is we connect this conductor to the earth, and then we ask you a question. The question asked is, calculate the induced net charge on the conducting sphere. That's the question I'm asking over here. Now, to calculate the net charge on the conductor, now it's kind of interesting. Over here, if this conductor was initially uncharged, then it would remain uncharged because there is no path for net charge to arrive on this conductor here. But in this problem, because we have connected this conductor with the earth, some net charge can appear on it because the earth can give it some charge. So now the charge on the conductor will not be zero, as you see over here. There will be some net charge which will necessarily be non-zero, and I'll explain why. We'll also be calculating the amount of net charge on this conductor. Now let's say some charge is induced on this conductor. Obviously it will be on the outermost surface, because the charge residing on a conductor has to reside on its outermost surface. Now I'm interested in calculating the potential due to the induced charges at the center here. So let's say in this part, so in this problem what we are discussing is the net amount of charge that appears on this conductor after it has been earthed. So to make this calculation, what I'll be doing is, I assume there is some charge, let's say Qi, net charge Qi on the surface of the conductor, and this tiny part of the conductor has a small amount of charge dq on it. Now because of this dq, the potential dvi at the center will be 1 by 4 pi epsilon naught dq by this distance, and that's r. So this is the potential due to dq at the center of the sphere. Now this dvi is the potential due to this element. Total potential vi at the center because of all the charge will be given by 1 by 4 pi epsilon naught r. Now r is a constant because all dq charges will be at the same distance r from the center. So r is a constant, it comes out, and we are left with an integral of dq. Now when we integrate dq, we do a summation of dq, we get the total induced charge, and therefore vi will be qi divided by 4 pi epsilon naught r. Now this is the potential due to the induced charges at the center. The potential due to this charge at the center can easily be calculated using the formula for a point charge, and therefore the net potential at the center of the conductor will be 1 by 4 pi epsilon naught q by small r. This is the potential here due to q, the charge here, and then potential due to qi at the center, that's given by qi by capital R. Now this total potential will be equal to, any guesses? Anyone making a guess here? Come on. This has to be 0. Now why so? Because the damn conductor is connected to the earth, and when we connect a conductor to the earth, its potential is necessarily 0. So this is 0, and therefore when we calculate this qi, we get minus q r by small r. So that's the induced charge on the surface of the conductor. Very interestingly, you will notice the charge on the conductor is not 0. So occasionally there will be books which will say the charge on an earthed conductor is 0. Not really. Not unless the conductor is completely isolated. Isolated meaning there are no charges in its neighborhood. So if there are no charges in the neighborhood of a conductor and you earth it, its charge becomes 0. But if it has charges in its neighborhood and you earth it, some charge actually appears on it because of the earthing, right? So very interesting problem, this one. Let's take up a few more, even more interesting problems. This time, let's consider a pair of concentric conducting spheres. So this time we are considering a pair of concentric conducting spherical shells. So this is a conducting shell having a radius A, then another one having radius B, and they're concentric. And by concentric I mean they have the same center. So we have two concentric, I'll write this down here so that you can remember, concentric conducting spherical shells having radii A and B. Now the outer shell has a charge Q on it and the inner shell is connected with the earthed. So we've done an earthing here, and as a result of the earthing, because this conductor has some charge in its neighborhood, because it has been earthed now, some charge Qi will now appear on it. Now we are interested in actually calculating this Qi. We are interested in calculating Qi, the charge which now appears on this conductor. Now to make the calculations for Qi, we'll be using the ideas, the concepts of potential. Now at this point here, let's calculate the net potential due to this Q as well as this Qi. So the potential V here, because of capital Q, this shell, will be 1 by 4 pi epsilon naught Q by capital R. That's how you calculate the potential at a point inside a shell. So the potential at this point due to this shell will be this amount. And the potential at the same point due to Qi, well, instead of R I should have written B over there, sorry. So this should have been B. Potential inside this shell, potential inside this shell due to its charge Q. This is what we get. At the same point, potential due to this Qi will be Qi 1 by 4 pi epsilon naught Qi divided by A, right? Potential on the surface of a shell due to its charge. So I'll use that result. And the sum of these two potentials, that is the net potential at this point, has got to be 0. Now why is that? Why does it have to be 0? It has to be 0 because the conductor has been earthed. And therefore, the induced charge Qi on this conductor comes out to be, putting this equal to 0, the stuff inside the bracket is 0, and therefore Qi is minus Qa by B. So we've calculated charge on another earthed conductor because it had some charge in its neighborhood. It was not an isolated conductor. And so when you have a non-isolated conductor and you earth it, some charge actually appears on it. So another very interesting problem here. Now the problems, kind of problems that can be asked on these ideas, they're pretty much endless. But I want to discuss one more very important kind of problem and then move on to the idea of capacitors. So erasing this here and then taking up the next problem. This time we have two parallel conducting plates. So we have this conducting plate here, we have another conducting plate here, so two parallel conducting plates. These plates have an area A each, and their linear dimensions are pretty large compared to the distance D between them. So the linear dimensions, that is the length and the width of these plates, is very large compared with this distance D. Now what we do is, these two plates having this amount of area, they are placed in front of each other, parallel to each other. And another very interesting, very important thing is they're completely overlapping like this, right? They're completely overlapping like this. They're not placed this way. Since it's a two-dimensional figure, you can't really make out. They're not placed like this. They're placed this way, completely overlapping each other, not in this manner. So please make sure you understand this. The areas are completely overlapping, and what we've done is we give them some charges. We are giving a charge Q1 to this plate, we are giving a charge Q2 to this plate, and what we are going to do is we are going to calculate the amounts of charges on these four surfaces: surface number 1, surface number 2, surface number 3, surface number 4. So how these charges are going to distribute on these four surfaces, this is what we are about to calculate. These are very interesting calculations actually. Now remember one thing: when we have conducting plates, the electric field lines have to be normal to or perpendicular to these plates. So if you draw any field line between these two, the field line will start perpendicular to this plate, end up perpendicular to this plate, and therefore they are straight lines perpendicular to both plates. See, why straight line? Why not a curve? Because the plates are very close to each other, and since the plates are very close to each other, the line doesn't really have enough space in here to go curving around and then finding a perpendicular intercept on this surface. So they're perpendicular to both surfaces because the surfaces are very close. If they are curving around and then again becoming perpendicular, you might say this is a possibility that they become perpendicular to both. But why would it curl around like this, especially when the space between the plates is very small? So the straight lines from one plate to the other, and therefore we have an easy calculation on our hands. All the field lines from this plate to this plate will be somewhat like this way. I'm not drawing the arrows, I'm not showing directions because we are not sure of the direction of the field, we are not sure of the nature of the charges on these surfaces. They may be positive, negative, we don't know yet. So the field lines will be somewhat like this, and since the conductor discontinues over here, if you come down here there will be no field lines. There is some bending of the lines around the corners, and that effect is called fringing, but we are going to ignore it because that happens in a very tiny amount of space, and therefore can be neglected. Now we have these lines, and there may be lines outside as well here. In this space there will be lines here. I'm not talking about those yet. We might talk about them later. Now I draw a Gaussian surface, a cuboidal shaped Gaussian surface like this. And all over this surface, over the entire surface, this entire Gaussian surface, what you'll notice is, well, there is no field here. There are no field lines here. There is no field here. There is no field here. And inside the conductor, in any case, the field has to be 0. So the field here is 0. Field here is 0. Field here is 0. Field here is 0. And so the flux through this entire Gaussian surface, the flux through this entire Gaussian surface is 0. If the flux through the entire Gaussian surface is 0, the net charge enclosed inside this Gaussian surface now has to be 0 as well. And therefore, the charges on these surfaces, on this surface and this surface, if at all they have charges, they have to be equal and opposite. Let me find the right color. The charge on this surface, if it is plus Q, then the charge on this surface will be minus Q. And since we have given Q1 charge to this plate, and out of this Q1 plus Q has appeared on this surface, the charge on this surface will be Q1 minus Q. And similarly, now we've given charge Q2 here, of which minus Q appears here, and therefore on the outer surface you have a charge plus, let's not use plus, charge here will be Q2 plus small q on this surface. So now we have a far better idea of how much charge is there on each surface, and if we are able to calculate the magnitude of small q, we will actually know the amount of charge on all of these surfaces. So 4 surfaces, 4 different charges, but they all depend on small q. And if we calculate small q, we have the charge on each of the 4 surfaces. Now to calculate this q, let's consider the electric field in the space between the plates. And to do that, what I'll do is I'll redraw this figure here so that there is less clutter. If I show everything here, there'll be too much clutter. So I'm drawing the plates all over again. Mind you, the distance between them is tiny and the areas are fairly large. Now what I'll do is I'll be showing the surface charge densities in all these surfaces. So on surface 1, 2, 3, 4, on surface 1 the surface charge density will be Q1 minus small q by the area A. Surface charge density on this surface is Q by A. Surface charge density here is minus Q by A, and surface charge density on this surface is this charge by area A. These are the surface charge densities. I made the correction there. So let's calculate the electric field in this region. Now at this point here, at this location here, the field due to Q due to charge on surface 2, at this point the field due to charge on surface 2, let's call it E2, will be given by sigma by 2 epsilon naught. See, what you have on this surface is a sheet of charge, and a sheet of charge produces this amount of field, sigma by 2 epsilon naught. Similarly, at the same location, the electric field due to 3, charged on surface 3, let's call it E3, will be given by same sigma by 2 epsilon naught, that's the magnitude, and since the charge is negative, the field is towards that charge. The sum of these two will be, if you add them up, will be sigma on any one of them by epsilon naught, correct? This is the sum of E1 and E2, and this is also incidentally the net electric field in this region. Now, how do I know that this is the net electric field in this region? This is the net electric field in this region because this is sigma by epsilon naught, and near the surface of a conductor, the net electric field, which is normally outward from the surface or into the surface depending on the sign of the charge, the magnitude of field just outside the surface has to have a magnitude sigma by epsilon naught. That we took up in the previous video. So the net field here has to be sigma by epsilon naught, and this sigma by epsilon naught is the sum of E2 and E3. That means the net field in this region, the net field in this region is the sum of the fields due to 2 and 3 only. The net field in this region is due to fields due to charges on 2 and 3. The surfaces 1 and 4, have zero contribution to the electric field in this space. Very, very important conclusion. Surfaces 1 and 4 contribute 0 to the field between the plates. Now we figured this out. Now I think the logic was a bit complicated, so you can go through this part of the video, last few minutes, review it and watch this as many times as is necessary to grasp the idea, and then get back to this point. Now the field in the space between the plates has a zero contribution from charges on surface 1 and 4, and therefore the fields due to this charge and this charge have a zero contribution here, which means that their fields in this region will be equal and opposite, contributing 0 to the net field in this region. These two charges contribute 0 to the field here, and therefore their fields in this region must be equal and opposite. And if their fields are equal and opposite, their sigma must be equal. If you have a sheet with a charge density sigma, the field is this way, and if you have another sheet with the same sigma, the field is this way. So they are equal and they are opposite. They have to be equal, and for them to be equal, the sigma has to be same, and therefore Q1 minus small q by A has to be equal to Q2 plus small q by A. This A cancels, and you end up with the Q equaling Q1 minus Q2 by 2. Now once you have this value of small q, you can substitute it here and get the magnitudes of charges on all the four surfaces. Substituting this q here, we have Q1 minus Q2, Q1 plus Q2 by 2. Here as well, if you add this small q, you have Q1 plus Q2 by 2, and this small q will be equal to Q1 minus Q2 by 2. Of course, on this surface it will be negative of the same amount. So very interesting problem this, and will be fairly useful in some of our discussions that are coming up later on in perhaps this video and maybe in the videos coming up. So very critical, this idea. I would suggest you watch this particular problem and the discussion on it, well, 5, 6, 7, 8, 10 times, as many times as you possibly can, and be completely sure of what's being discussed. I can vouch for the complete accuracy of this. Watch it a number of times so that you're absolutely certain of understanding the ideas discussed here. So moving on from here, we'll be taking up the concept of capacitance, and that's our next discussion. What is a capacitor? But before we can have this discussion on a capacitor, just a little word on what is a battery. Okay, so just a brief discussion on what's a battery. Well, a battery is a device which maintains a constant potential difference between 2 points called its terminals. Now, a battery is a device which, through whatever means, you probably study that in a chapter on electrochemistry, a battery is a device which maintains a constant potential difference between 2 points, which we call its terminals. So the terminals of the battery are like this. They are represented by these two lines. The smaller line represents the terminal at the lower potential, and the longer line represents the terminal at the higher potential. So this terminal at lower potential is called the negative terminal, and this terminal at the higher potential is called the positive terminal. The difference between the potentials of these two terminals, V, is called the EMF of the battery. So this is the potential difference between the terminals, and it's called the EMF of the battery. Now, interestingly, this nomenclature EMF stands for electromotive force. Now, it's actually a misnomer, because this potential difference is a potential difference and not a force. But since the idea developed at a time when the concept of potential was not very well understood, people in those old times chose to call it electromotive force. The belief being that the battery kind of gives the electrons a push to cause them to move in a circuit, and therefore the name electromotive force came up, which seems to kind of indicate that it's a force, but it is not. It is a simple potential difference. So if the EMF of the battery is V, the potential difference between the two terminals will also be V. So that defines for us a battery. More details on battery will come up later on when we take up this chapter on current electricity. But for now, let's keep our focus on the idea of what is a capacitor. Now, consider a conductor. This is a conductor. It may be solid, it may not even be solid, it may be a hollow conductor, doesn't really matter, because we know that in case of a conductor all the action is on the surface. We then connect this conductor to the positive terminal of a battery, and the negative terminal is then connected to the earth. The EMF of this conductor is known to us. It's given to be V. So EMF of this conductor is V, which essentially means that the potential of the positive terminal is V more than the potential of the negative terminal. Since the negative terminal is connected with the earth, the potential of the negative terminal is equal to that of the earth, which means potential of the negative terminal is 0. The potential of the negative terminal is 0. Why? It's connected to the earth. And therefore the potential of the positive terminal is V. Potential of the positive terminal is V, and therefore since the positive terminal is connected to this conductor, its potential is also equal to V. Now, since this conductor has a potential, it must have some charge as well. And since the potential is positive, the charge is positive too. So it has a positive charge on it. Now, a quantitative relation between this Q and this V. Remember, the potential of this conductor is V. The charge on it is Q. And we know, kind of experimentally, that this Q is directly proportional to V. This Q is directly proportional to V. Now, converting the proportionality relation into an equality relation, we get Q equals some constant C times V. Now, this constant C is called the capacitance of the conductor. Now, the statement here seems to, kind of indicate that this C is the capacitance of this single conductor alone. But that is absolutely never the case. A single conductor cannot have capacitance. You always need two conductors to generate capacitance, and mind you, the other conductor here is the earth. Okay, so we have two conductors, the earth and this small conductor, and together they have this capacitance C. It depends, of course, on the geometry, the shape and size of the conductor, and the way it is oriented with respect to the earth. So it's a constant here, and this constant is called the capacitance of the conductor earth system, actually, not just the conductor. Now, this C equals the charge induced on the conductor per unit potential of the conductor. and that tells you, that's the definition of capacitance. It's constant for a conductor-earth pair, okay, and it has a unit that is equal to Coulomb per volt. Now this Coulomb per volt has been given a name, Farad, named after Faraday, the great British scientist. Read his life story, very interesting life story and history there. Perhaps more on that in some other video. So Farad is the unit of capacitance. Mind you, this Farad is an enormously large unit. So Farad is an enormously large, very, very large unit, and it's really almost impossible to create a capacitor which would have a 1 farad capacitance. Practical units of capacitance are microfarad, nanofarad, picofarad, etc. And those are the capacitors that you will be dealing with in practical applications. Also in your problem solving, you'll mostly deal with capacitors with capacitance of either microfarad or smaller than that. Now this is for an arbitrarily shaped conductor, but since we are somewhat familiar with the spherical shape, we can actually do some interesting work on spherical capacitors, but more on spherical capacitors. One little thing that I might have forgotten to tell you about is that this capacitor not only stores charge, it also stores energy. So in fact, that's what a capacitor does. It's a device that stores charge as well as energy. Now how much energy does this particular capacitor store? We'll need to make a calculation of this. Let's say we have this conductor, the same conductor maybe, and let's say the capacitance of this conductor in Earth system is C, and we are charging it by bringing in charges in small installments of dq each, and we are adding this dq onto this capacitor 1 bit at a time. After some time the charge on it has built up to Q, but we still keep adding more and more, and eventually a total charge Q has been built on this capacitor. The capacitance is C, and therefore when the charge on the capacitor is Q, its potential V will be given by Q by C, right? That's the definition. Potential will be Q by C. So when the charge on the capacitor is small q, capacitance is C, its potential is Q by C. And we bring in a charge dq to the capacitor now. So the potential here is so much. We add a charge dq, and the potential energy changes by du. Now you're probably remembering, you're easily able to recall now that this is how we calculate potential energies of systems. We build up the charge on the system a little bit at a time, and in each step of the way we calculate the change in potential energy, and then we do a summation of all those changes to get the final value of the potential energy. So potential energy here will be 1 by C Q dq. We are doing a summation of the du to get u, the final potential energy. Now the limits for Q will be 0 all the way up to capital Q, and therefore the potential energy comes out to be, I'm skipping some elementary mathematics, Q square by 2C. Or since Q is equal to CV, it's also equal to half CV square. So we've learned how to calculate the capacitance of a conductor and also the energy on it. And since we are now fairly familiar with the spherical shape, let's try out these calculations for a spherical conductor. Just to get a grasp on these ideas, we will now be calculating the capacitance of a spherical conductor, also the energy on it, and try and see if the results match up. So, spherical conductor now. So we've got a spherical conductor having a radius r, and we connect this conductor to the positive terminal of a battery of EMF V, and the negative terminal is connected to the earth. So once we made these connections, what happens is there's a transfer of charge Q from the earth onto this conductor. It now has a charge Q on it, of course transferred by the battery, and now the potential V of the conductor, the potential of this conductor has to be V now, of course. The negative terminal has potential 0, the positive terminal has potential V, and therefore the conductor has potential V. I'm repeating the same arguments we did with the conductor of arbitrary shape some time back. So this has a charge Q now, and this Q of course equals, the potential of the conductor, which is V, now equals Q by 4 pi epsilon naught r. This Q charge appears entirely on the surface, so it's a shell of charge Q. A shell of charge Q produces this much potential on it. Now, this V is of course also the EMF of the battery. Remember that later on we'll be talking about this a little more. Q therefore equals 4 pi epsilon naught R times V. Reminds you of the relation Q equals CV, and therefore C, the capacitance here, is 4 pi epsilon naught R for this spherical capacitor. Now we've calculated the capacitance, and I bring you back to the idea we just discussed that 1 farad is an enormously large capacitor. Now 4 pi epsilon naught is 1 upon 9 into 10 to the power 9. So this is of the order of approximately 10 to the power minus 10. So to have a capacitor of 1 farad, it has to have a radius of the order of 10 to the power 10 meter. Now 10 to the power 10 meter just happens to be about 10,000 times the radius of the earth, and that's an impossibly large sphere to construct, and therefore 1 farad is an impossibly large capacitance. Now we've got the capacitance C. What's the potential energy stored here? The potential energy stored here is the self energy of this shell, which will be Q square by 8 pi epsilon naught R. Right? You remember the formula for self energy of a shell. This is what we get. And oh my, this matches exactly with Q square by 2C. Can you see 2C over here? This is C, and easily seen that this is 2C. So the results are working perfectly. After all, it is physics. It works, and works pretty perfectly, pretty beautifully. Now another interesting thing to learn here is that when charge Q moves from here to here, its potential is increased by an amount V by the battery. And when the potential of charge increases by V, its potential energy increases by Q times V. So the increase in potential energy of the charge, is Q times V, which is, oh my God, again very interesting. This is CV times V, and so CV square, or you can say Q square by C. This increase in potential energy of the charge was achieved by the battery, and therefore this is also the work done by the battery, right? Work done by the battery. Now this battery seems to be performing more work than the stored potential energy. In fact, in this particular example, work done by the battery is exactly twice the stored potential energy. And that's kind of confusing, isn't it? Well, it really shouldn't be, because the charging happened when charge flowed through the wire. And when charges flow through wires, what happens is heat is produced. You've learned this in your earlier classes as well, that heat will be produced when charges flow through wires. So we've applied this idea of capacitance in case of spherical capacitors. And now that the video is beginning to get a little long, we'll bring it to an end. And in our next video, we will be talking about parallel plate capacitors and their combinations. But then that comes up in our next video. This video I'm bringing to an end here, getting a little too long perhaps, and therefore I will thank you for watching this video and remind you to like, share and subscribe one more time to support this channel and to keep me encouraged to do more work for you in the time to come. Thank you so much for continuing to support the channel. Bye-bye till we meet again.